Hi, everybody. So I'm Gabriel Synnaeve, research scientist and manager in Paris, and I'm going to talk to you about AI research at Meta. So, for a brief history, Yann Lequin founded Facebook AI Research in 2013 as a research lab that focuses on fundamental research. He then got the Turing Award in 2018 for his pioneering work in deep learning alongside Jeff Hinton and Yoshua Bengio. FAIR now is spread across a lot of locations, 5 in the US and Canada, 3 in Europe, as well as remote employees. And FAIR is part of a broader Meta AI organization focused on developing and leveraging AI for all of Meta. So the research areas that FAIR operates in includes core ML and theory, vision, speech and audio, NLP and machine translation, reinforcement learning, robotics, AI for science, creativity. And here are a bunch of examples of Meta AI projects. Our organization in particular is researcher-led with a strong focus in science and engineering excellence. And we value impact through open science. We have collaborations with the industry and academics alike. And we have some research projects that make it into the product, some research projects that kind of have some influence on the product roadmaps, and some research projects that have absolutely no influence on the product but still are worthwhile research projects for FAIR. I'm going now to cherry pick a few projects just to briefly tell you about. So this one is basically at Facebook we serve more than 200 languages for Facebook and Instagram. We provide translation for several of them. But there is a team called the No Language Left Behind, a team that works on developing translation to and from all of them and directly. Similarly, recent wins at 2 premier translation competitions for both text and speech translation. We demonstrated that a single multilingual system truly is better than bilingual systems. So it's a single system that translates from any language to any language. We did that by increasing model size through a mixture of experts, producing more training data, scaling back translation, and we basically demonstrated that multilingual translation is a promising way forward. Here is a completely different project where we train seek-to-seek transformer models to symbolically integrate mathematical functions. So how does it work? We take the mathematical expression on the left, we tokenize it by following the parse tree. We also, as you see on the left, we also then tokenize the integers and floats, as you see on the top right. And finally, we use that kind of in a vanilla translation task where you take as input the function, as output the symbolic integration. And it's quite correct most of the time and gives answers faster than Mathematica, for instance. Totally different register. And let me tell you about some recent progress in self-supervised learning. With an example from computer vision. So in this video, you can see the input images and then the transformers model attention corresponding to a given object. What is really striking is that this model was not trained with any labels and was not trained also on videos. It was trained on still images, namely ImageNet. Still, you get temporally consistent object tracking for free. And if we compare here the exact same attention of the same model, so it's a vision transformer, trained supervisedly or unsupervisedly, you see the features are much higher quality in unsupervised fashion. So the story everywhere is that we try self-supervised learning approaches, so being it vision, speech, NLP, is that we get high quality features that can directly be reused or fine-tuned in downstream tasks. This allows us to get state-of-the-art performance either with less labeled data or tackle new applications with less labeling effort. Okay, so finally, let me tell you about a project that is closer to me because that's one where I directly worked on personally as a researcher. Basically, it's how can we generalize beyond the training set? For instance, if you never labeled a pink elephant, or even harder, you have a vision system and you never saw a pink elephant in your training images, right? So you're still able to imagine what a pink elephant looks like as a human, right? And you can do that. One of the reasons is through composition of language. So we designed an object detection model that can leverage free-form text as a form of supervision. And when we probe it on this image, where actually the colors are not simulation mask or anything, we really colored an elephant pink and another one blue, and we ask it to find the pink elephant, it finds it. The way it works is basically the model probably saw in the training set pink objects, pink cars, pink, I don't know. And it's also so elephants, maybe even gray elephants with a color attribute. And due to the free-form task supervision, it can do the composition of pink and elephants right off the bat without any retraining. It still has some failure modes, which are quite interesting. So if you ask it to label a normal elephant, well, it has no precomposition, no like common sense knowledge of the world. So everything looks like a normal elephant. It was never trained to say, okay, pink elephants are not normal. So there is this kind of closed world assumption underlying all of that. And still, if you ask it a normal elephant, it's going to show you a normal elephant everywhere. There is a way to fix that, but it's to be exhaustive. If you are exhaustive and you say, okay, label me a pink elephant, a normal elephant, and a blue elephant, then it works by the exclusion principle. And that's about it. So it was 5 minutes about AI research at Meta. If you want to know more, or if you just want to chat, feel free to reach out to me or to Pierre-Louis Chess, who's here also, or feel free to come see us at the booth upstairs. Thank you.
Thanks so much.